Good evening to all of you. We are back again with another exciting session. I, Ajay Jha, on behalf of ACS India team, welcome you to today's session. Just to update you on the upcoming ACS Science Talks, please feel free to visit our ACS India webpage where you can see the upcoming ACS Science Talks and register for these sessions. We have also uploaded the past lecture recordings in the ACS Science Talk virtual library section. Please go through these, share among the scientific community, and get benefits from it. To update you on the upcoming events, the breakthrough science at ACS, the product launches at ACS, we have ACS Insights India newsletter, which is free. Subscribe today using this QR code. We'll put the subscribe link into the chat box for your convenience. Now moving on to the scientific session, we are pleased to have Professor Ramesh Gardas with us. Professor Gardas completed BSc, MSc, and PhD in chemistry from the Veer Narmad South Gujarat University. Then he joined University of Coimbra, University of Ivro, Portugal, and Queen's University, Belfast, UK, for his postdoctoral research. He joined the Indian Institute of Technology, Madras, India, in 2010 as an assistant professor in chemistry and promoted to associate professor in 2015 and to full professor in 2020. Professor Gardas' research group focuses on chemical thermodynamics and phase equilibria of industrially important solvents and their mixtures. More than 7,500 thermodynamic data points measured in his research lab are included in NIST standard reference database developed by Thermodynamics Research Center, NIST, USA. One of his developed models is extensively used by the peer review scientific community as Gardas-Corteno model. In recognition of his outstanding performance as a researcher, Professor Gardas has been bestowed with several awards by prestigious institutes, societies, including the Mid-Career R&D Award 2020 by IIT Madras. Recently, he has been recognized as Associate Editor of the American Chemical Society Journal, Journal of Chemical and Engineering Data. He is a Fellow of Royal Society of Chemistry, UK. He is among the top 1% reviewers in chemistry and has been listed in Publons in 2019. He has been featured in the list of world rankings of top 2% scientists in 2020 database created by experts at Stanford University, USA. Before Professor Gardas starts, a few instructions for the audiences. We request the audience to post their questions into the Q&A tab and avoid putting questions into the chat box. And in case of any internet interruptions, please stay with us. Now, I would like to invite Professor Gardas.
So, first of all, I would like to thank entire ACS India team for giving me this opportunity on ACS Science Talk virtual lecture series. I'm delighted to talk in this series of the lectures. And today's my talk is on alternative solvents for sustainable development. I divided talk into two categories or two parts. The first part, I will talk general about the solvents and why we need to look for alternative and what are the selections criteria. In the later part, I would talk on my research where ionic liquids, how this can be one of the alternative solvents for volatile organic compounds. Let's see how I can justify the time within 35 minutes or 40 minutes for the both parts. First of all, I would like to share that I am delighted to join ACS Journal of Chemical and Engineering Data team. This is a new team from January 2021, and I'm happy to work with them. And this journal is primarily concerned with the articles containing data, both from experimental part as well as computational part on phase behavior, physical, thermodynamic, transport properties of well-defined materials, including complex mixtures of known composition. And as Ajay introduced me already, I'm from chemistry department at IIT Madras. We have a beautiful campus. If you happen to visit Chennai or South India, please do visit our campus. I would like to thank all my former students and present students and my collaborator in the department, in the institute, in the country and across the globe. And I would like to thank ACS Science Talk virtual lecture series, and my department, institutes, and funding agency, and a few of the websites from where I have taken many of the images what I'm going to present today, from ACS, RSC, United Nations, and some from Google, so on. I do not claim right of any of these images what I'm going to present. As much as possible, I have cited the link. If not, please consider this is from one of these 4 websites. I would like to begin with this logo. You might be knowing, and these are the 17 colors. Each one represents for one goal, and this is United Nations 17 Sustainable Development Goals. And the vision has to reach by 2030, and UN has requested many societies and researchers and the countries and their scientific teams to work towards this sustainable development goal to achieve by 2030. What is this sustainable development? If I may break down into a simple term, any development which is economically viable, environmentally acceptable, and socially equitable, that kind of development can be called as a sustainable development. And something similar to Newton's third law. If you protect nature, then only nature will protect you. If you care for nature, then only nature will care for you. And we go forward. United Nations Global Chemical Outlook 2, which is published a couple of years ago. It's a mammoth 700-page report, and it tells the importance of sustainable development. And one of the statements from there, the global chemical industry sales exceeded $5 trillion in 2017 and are expected to double by 2030. That means we have a tremendous opportunity in this chemical industry, and the chemist has to play a key role. And in this chemical industry, when they want to go towards sustainability, chemist has to play a crucial role in all 3 stages. Before starting the reaction, let's say the reactants choice, and during the course of the reaction, how to optimize the parameter, and the end of the reactions. You don't want byproducts, and you want the products or the main products as much as yield possible. In all 3 stages, chemists can play a crucial role, not only for reactions, but for process and product designs. They can give input parameters. Well, apart from that, if we take forward, I will give you one example. There will be many examples, but let me say one example. If you take a smartphone functioning, for the better functioning of the smartphone, one need to have idea of the physical and chemical properties of more than 50 atoms in the periodic table. Either they're in pure state, or they are in a compound or a mixture with another state, be it a screen or a battery or a case or a processor. So that's how the chemistry is involved in all the industrial development. I'm not going, there are plenty of examples. Let's say if you sit on office chair, the chairs, polymers, or the textile, or dyeing, or a pattern, everywhere the chemist has to play a role in designing and modifying and all these things. Apart from that, any innovation or any development, when you want to go for the globalization level or the large scale, so it need only possible by collaboration. Either academia and industry and the government sector all should work together for the innovation and then execution. Recently, last week, Chemical Industry Outlook by Indian Chemical News has highlighted this. Apart from government and the academia and the industries and the private sectors, civil society and the citizens also has to play a crucial role to achieve the sustainable development goals. And the green chemistry that prioritizes safety, improving energy efficiency, and the most importantly, minimizing the toxic waste. However, the sustainability is only peripheral in education, and that too in the postgraduate education. This from elective courses, it has to go into the core courses, not only at the postgraduate level, probably at the graduate level itself, or maybe at the high school level. Students should learn about the sustainability and its importance. One of the very recent, 2 weeks ago, or March 1st, this editorial published in ACS Sustainable Chemistry and Engineering. One of my colleagues is also on the board, Professor T. Pradeep. And this article from lab to market highlight the ACS Green Chemistry Institute survey on how sustainability metrics can be used in the chemical industry, and they can promote this technology towards green chemistry and how to reduce the environmental footprints. Many of the well-known companies such as Dow, BASF, DuPont, and Procter and Gamble, and few more have used this, and they have got benefited, and that has, which can be seen from their annual sustainability reports. And that's a good news. But what is happening is not enough, and we need to take it forward. Whatever today we are seeing in most of the global value chains are a linear economy. We need to promote more and more from this linear to circular economy. So how we can transform this linear economy to circular economy is the key. And how solvents will play a role, I will tell you. Coming back to the solvent, if you see the petrochemical based solvent market is more than $57 billion, and compound annual growth rate is 4%. And if you see, that is something like 37,500 kilotons of by volume per year. And this is due to high demand in three sectors: automotive sector, construction sector, and the energy sectors. However, due to stringent environmental regulations, all these companies have been forced to look for alternative solvents, probably greener solvents or biosolvents. So nature has a solution close to the nature, and that's where people go more towards bio. And one of the very well-known and more eco-friendly solvent recently came into the market is a serine, which is a cellulose-based solvent which can replace many of the dipolar and aprotic solvents. Well, next 15-20 minutes, I would talk about, or 10 minutes about volatile organic compounds, how can be replaced, and then 10-15 minutes on ionic liquids. So without wasting much time, let's go into the talk. Let me start with understanding what is green chemistry. If I can read this, the design, the development, and the implementation, all three parts. So designing, that is in the beginning and during the course of reaction, and then implementing in the larger scale of chemical products and process that either reduce or eliminate completely. So use or a generation of hazardous substance. So hazardous substance should not be used from the beginning, should not produce either during the course of reaction or at the end of the reaction as a byproduct. If this has been taken care, and that chemistry can be considered as a green chemistry. And if you see the 12 principles of green chemistry, solvents play a crucial role in executing or in fulfilling most of these principles, including the safer solvent itself is at the 5th stage, but other places also solvents play a very, very crucial role in atom economy or other places. Well, similarly, 12 principles of chemical engineering. I'm not able to see my full screen. Okay. So including chemical engineering, 12 principles of green chemistry, chemical engineering. So now I told you about 3 numbers. 1, United Nations Sustainable Development Goals 1 to 17. 12 principles of green chemistry 1 to 12. 12 principles of green engineering 1 to 12. These 3 numbers are very crucial when you are going to write a large proposals or international bilateral or trilateral or multilateral proposals, and what goal or towards which goal you are going to focus on your in your proposal, or what is your target, and this will help a lot. So I'm trying to have a full screen, but this is visible. What is happening? I'm checking. Looks like if somebody asks question, this is going left. Anyway, we know generally we think that solvent means it used to dissolve solute, but not like that. Solvents has a major part to play, even if it is extraction or purification or changing some parameters of the solutes. I will talk more in detail later on, but the solvents are a key priority when green chemistry is in the picture, because they are used in high volume and many of them are volatile organic compound. Due to this volatility, or what you call large vapor pressure and less solubility, they create so many problems, including air pollution, ozone depletion, global warming, climate change, and so on. So we need to look for a renewable solvents which are not derived from petrochemical, or we use 3R principle: reduce, reuse, and recycle. Or you look for alternative which will be highly potential for recycling and then stable. And any chemical industry or any academia, the rule is simple, or the business model, what you call low cost and high yield. That is minimum investment and maximum profit. How it could be achieved, keeping in the environment or green chemistry aspect in intact. When we say solvent, why we should worry? Generally, we look for solvent if you want to modify solute properties, or you want to isolate certain products or remove impurity or to promote the chemistry. Well, is this enough? The thumb rule says, I'll come to that, but when you look for same solvent work for all these things, and it also belong to the green chemistry, or it should be eco-friendly, environmental friendly, benign, or sustainable, then we have to look into varieties of the things, like we want in protic, aprotic nature, different polarity nature, different basicity nature, and above all, we need a combination of these three, and that creates a challenge. Well, the thumb rule says, or when we look for a solvent, we look for only temperature window or functional group or the polarity. But the ACS Green Chemistry Institute come up with a great mission which states that to catalyze and enable implementation of green and sustainable chemistry and engineering throughout the global chemical enterprise and across the society. And they have so many round tables I'm highlighting here, and including solvent selection tool. So this is one of the greatest round table from the ACS Green Chemistry Institutes, which have solvent selection tool. I will show a couple of slides from that. And as I told you, we generally look for only three things when you look for solvent. What is the temperature range between melting point to boiling point? What are the functional groups available? And what is the polarity? Can we look beyond this? Okay. Should we not look for their legal controls, environmental impact, health and safety performance, and other properties and other functionality? Is it available in the large scale if you want to perform, or when the research grows from the laboratory scale to the R&D scale to the pilot scale to the industrial scale? Do we is there any problems in the availability or the transport or so on? Should we worry or not? Well, if you see the Kamlet-Top plot of basicity versus polarity of the well-known industrial solvents, both protic and aprotic solvents, the spectrum is full. Whereas environmental benign solvents are very, very less. So it's our duty as a scientist and engineer to fill this entire spectrum. Then we can show the industry, why don't you look for an alternative? This might work because this fall under same basicity and same polarity. So we need a large pool of the new solvents. Well, from the existing solvent itself, it is known that in industry, there are around 300 well-known solvents used in the chemical and related industries. Out of this 300 itself, can we look for alternative? And how it is possible? Well, as I told you, this ACS Green Chemistry Institute has come up with the solvent selection tools with different input parameters. From 272 solvents, you can screen the solvents which may work for your reaction condition for a good yield and without impacting on what you call environment, or with the less impact compared to other solvents. How? Let's say take two scenarios. One scenario, we don't know about which solvent will work at all, and it's a new reaction and you don't know anything about the solvent. That is the first scenario. Second scenario, you already know what solvent is working, but due to environmental and legal or legislative restriction, you are looking for a replacement. In both cases, you start uh, this selecting solvents and define what kind of temperature window you may prefer, what kind of chemical incapabilities or which groups will work, and which country you are and what regulatory aspects you are looking for, and what is the solute specific refinement. Are you looking for polarity? Are you looking for basicity? Are you looking for a dissociation constant? Are you looking for some viscosity, physical property? So you can choose the functional group, physical properties, and the principal component analysis. Also, you can have some engineering aspects in that, energies you can put, and then you can also take care of international, what you call ICH guidelines, International Conference on Harmonization, and also SHE guidelines, whatever safety, health, and environment issue. And you put all this information in this solvent selection tool, and you will get shortlist. And further, you can use either by simulation or experimentation, further reduction possible. I only gave a screenshot of the last slide, but it has give you the proper choice of solvents, let's say 2 or 3 or 5 from 272 solvents. Well, similar to this, Chem21, public-private partnership company from Europe, it is also distributed all the industrial important solvents into 6 different categories, from the dark green to the light green to the yellow and to the red and the dark red. So recommended highly hazards. In this category, they have shortlisted, and they have also come up with the different regulations and the group wise. So environmental, health, and property wise, and will it work or not. So that was the paper, Green Chemistry, RSC journal, and published about 2016, 4 or 5 years ago. But the website is more updated, and you can put it in ascending order, descending order of the family, or the boiling point, or the safety score, or health score, or environmental score. And this is very much user friendly, and you can look for alternative for your own solvents and to replace with the other particular solvents in the same family. However, this 270 or 300 working, is it enough? Maybe not. Where the demand of these solvents are very high, and in this industry they are in a various composition. We are not only talking about the pure solvents. They might be mixture of 2 solvents or 3 solvents, or binary, ternary, or multi-component mixture. So we need to have a varieties of the solvent feasible. Instead of using 3 or 4 different solvents mixtures, can we replace with the one single solvent which is different than this 4? So we need to build the library or the class of new very large solvent streams. One such example might be ionic liquids. There are so many things are coming, like supercritical fluids. You can use deep eutectic solvents, you can use, or you can do the reaction in water or without solvent. I'm not going into any of that, but let me restrict my talk to the ionic liquids. I put a quote here: old wine in a new bottle, because this is the new class of well-known molten salts. Molten salts are known for ages. We know that sodium chloride is in liquid state beyond 800 degrees Celsius. So we are talking about the salts which are liquid at and around room temperature. This possess so many unique properties: negligible vapor pressure, large liquid range, and large electrochemical window for battery and supercapacitor and electrochemical applications, high ionic conductivity, high solvating capacity, and above all, great varieties of the structure possible. Here I put one more word, that is hybrid salts. We know generally salts both are inorganic nature, cation and anion. Now we are talking about the salt where preferably one of the ion, preferably cation, is organic nature and the anion is inorganic nature. And the size, if you see common salts, not too much different cation and anion size, but here there is a large difference between cation and anion size and the symmetry and organic and inorganic dual nature. And due to these three things, one of the main reason out of why these salts are liquid at room temperature. And more than these heterocyclic compounds, you can have alkyl chain length attached to these cations most of the time. Sometimes you can have alkyl chain length to anion also. And due to asymmetry in shape, and you have a small as halide, or you can go for borate, hexafluorophosphate, or nitrate, or triflate, or bistriflamide. So due to variation in the size, and now you have three things you can change or tune. One is anion, two is cation, and the three is alkyl chain length attached to this cation or anion. So based on these three, theoretically, millions of ionic liquid feasible. And that's how theoretically feasible. And as I told you, due to asymmetric shape, they do possess some interaction due to ionic and covalent and other kind of interaction, but they cannot come closer and closer. One of the main reason for them to behave like a solid or remain in the liquid at room temperature. These are different than ionic solution. In ionic solution, the ions are surrounded by the solvent molecules, but in the ionic liquids, ions are surrounded by their own ions and they are in the liquid nature, and that's the beauty. This example might be you put a sodium chloride in water, you can make ionic solution. That's not we are talking. We are talking about ions are surrounded by their own ions and they are in the liquid nature. Well, compared to organic solvents, so far we know about 100 organic solvents, though industrially important are 300, but ionic liquids are more than millions on paper, or theoretically you can make, and reality studied also as many as the organic solvent or even more. And they are multifunctional and they possess unique combination. Having said so great about this class of liquids, if somebody asked me what are the limitations of this class of liquids, two major limitations. One, viscosity. Viscosity of this kind of liquids are much higher compared to organic solvents. Once viscosity is high, wherever you need a uniform mixing, stirring, heating, pumping, transporting are involved, the cost will go high, or you may not achieve uniform mixing or uniform heating. That is one problem. The second one is cost of this ionic liquid compared to organic solvent. For most of the ionic liquids are expensive. Very few which are comparable with organic solvents, and but we can address both this, like what we say in Hindi movie dialogue, ek teer do nishan. So we can address both problems in a single shot. Instead of using pure ionic liquid, we can think of their aqueous solution or solution in organic solvent. Now, this brings up another question. One side we want to replace volatile organic solvents, and other side now I am talking about adding a solvent. This may alter the properties of the solutes. Yes, it will alter, but it will reduce viscosity, it will reduce the cost. Then how it will be beneficial? If it can reduce the overall use of volatile organic compound, and with the same optimization or the better optimization of the process and product design, and without compromising the final product or the final yield, if it is working as an additive or a dissolvent or extractant, that's well and good. And that's where I'm talking now. Instead of using them in a pure state, can we use them in a smaller quantity along with the existing system? You do not change your system at all. No industry would prefer to change their entire system, which is well set up, which may take years and years or maybe decades. So in the existing system, if you add them, will it help? And that's where we were focused more in our research group. Well, if you see the applications, about 3 decades ago, it started as a just electrolyte and then shoot up with the solvent, extractant, lubricant, catalyst, and whatnot in many fields. And that all due to their unique properties, and not one or two, it's a combination of various properties. Some of them I listed here, I already spoke. If you see SciFinder, it shows More than 86,000 publications are there in this field, and more than 17,000 patents and 50 books, and so on. Something similar numbers from Scopus, probably conference proceedings or the thesis or book chapters may not be, or the patents may be varied, but overall same numbers. About 75,000 documents until yesterday. The precise number is here. And the field is not saturated. There was a time in 2010, 11, 12, people were telling, no, this field has gone to saturated. No, it has gone to that parabola. So you see the history. Anything new topic come, it shoot up, go slightly narrow, or the what you call constant, or slightly down, and again shoot up. And this is now the stage. It is picking up the industrial scales. And these are the few authors across the globe. I highlighted two: Joan Coutinho from Portugal, Chris Hardaker from UK, because I had opportunity to work with them during 2010, 2005 to 2010 as a postdoc with them. And you see the popularity of this field. Tom Welton's review paper. Tom Welton is at Imperial College, London, and he's currently president of Royal Society of Chemistry. His review paper published in 1999 crossed today more than 11,600 citations, a single review paper. And that shows the popularity of this field. And across the globe, many countries are working on this field, including India. In the last decade or so, we are at the third position in India. I don't want to compare among the countries because it depends on the GDP, it depends on how many number of researchers and how much. I'm not going into that part, but overall, if you see, we are above 5,000 documents and that third position. And the good thing is, across the country, all the parts, north, east, west, south, more than 150 institutes working on this field, be it the chemistry, inorganic, organic, physical, analytical, environmental, or chemical engineering or other engineering. And that's a good part. And many people are working on this field. Not only chemistry, as I told you, globally, chemical engineering, materials, physics, biochemistry, pharmacy, and so on. You might wonder why a single field got this much attention from so many varieties of the subjects. I do not wonder, because if you allow me to distribute entire scientific research into three categories based on the phase, like solid state research, solution phase research, and gas phase research. I have no hesitation to say that solution phase research is dominant over the other two, probably whatever the reason, easiness in handling or maintaining temperature, pressure, or the good environment, or work closely to the environmental condition, or heating, stirring, pumping, or transporting easy, whatever the reasons. But the solution phase science is known, and wherever solution phase science is coming, solvents are there. Wherever solvents are there, volatile organic compounds are the issue for the environment, and people are looking for alternative solvents. And that could be the reason this ionic liquid field got so much attention. Well, it is not only on paper 86,000 or only patent 17,000 or only 50 books, but it's reality. It has gone from laboratory to R&D to pilot to commercial scale. This is a German-based company, Ionic, and BASF German-based company. These are the few examples, but the exhaustive list, entire list until the last year. This book was published last year, and they have taken the applications, industrial application, commercial application until 2019. And this author is one of the best author to write this kind of book, because he worked in a company for a large time, and then he joined academia, University of Kansas, Mark B. Shefflet. He has a lot of experience, both from industry side and now from academia side. And you see, there are more than 29 applications at the pilot scale, 28 in commercial scale. In one of the conference, he also told there are so many in pipeline, and the companies would not like to share because of confidentiality, or they are still waiting patent to approve. So in the next forthcoming decade, or even less than a decade, these numbers might be twice or even more than that. Well, having said so great, what we are focusing, even though you have this field has achieved this much success, we still believe there is much more to understand the basics, how these special liquids or how their structure property relations work. And we at IIT Madras would like to understand this through solution thermodynamics or through physical chemistry, through thermodynamic properties. And these thermodynamic properties, any process or product design or any reaction or any research, when you want to take it from laboratory to R&D to a pilot to commercial scale, when the parameter can go significantly multiplied numbers, and that time accurate knowledge of thermophysical properties fluids play an important role in the cost-effective design and operation of chemical or biochemical plant. Of course, the accuracy depends in where you are going to use and whether impurity will matter or not, and that is a different story. But in most of the time, you need high accurate data. Well, many companies are selling this ionic liquid, TCI, Solvonic, Sigma Elrich, Fluka, Mark, Iolytex, Cytec, BASF, but only well-known ionic liquids. We never purchased any ionic liquid from any of these companies. Two reasons. We want to synthesize newer ionic liquids, and report says instead of buying ionic liquid, you buy a raw material and then synthesize in the laboratory, the cost may go 10 times down. Well, we are not an organic chemist. We are not an expert in synthesis, but ionic liquid synthesis is not difficult. Often it is a one-step acid-base neutralization or 2-3 steps metathesis or anion exchange. It's not difficult. The difficult part is purification and handling them, characterization and handling. Well, in the last decade, we were successfully synthesized more than 100 new ionic liquids. We have reproduced with the known synthetic procedure for more than 50 ionic liquids. So we have overall 100 plus 50, more than 150 ionic liquids. Well, it's my 30 minutes. I may take 5 to 10 minutes and then I can maximum 10 minutes. Then we can have a time for at least 10-15 minutes for question answer. Let me go to the next. What is a thumb rule? Most of the time it will work. Before synthesizing ionic liquid, can we predict will it be a liquid state or a solid state? Say the thumb rule says from this PCCP paper, Watanabe, very well-known guy from Japan, and when Lewis acidity of the cation and the Lewis basicity of the anion source both are low, resulting salt will be a liquid. If both are high, it will be solid, and this works in most of the cases, including our cases. And if it is only mix match, then you need to look for more chemistry. These are the few samples. Most of them are before purification, only few are after purification. So as I told you, synthesis is not a difficult task. The difficult task is a purification and characterization and handling. And what after all this, we study their thorough thermophysical profiles, like volumetric properties, transport properties, acoustic properties, thermal properties, surface properties, interfacial properties, refractive properties, and then derived properties like expansibility and compressibility. We also work on phase equilibria like solid liquid, liquid liquid, vapor liquid. We are about to just start it this year only. And then this all data is essential for whenever this solvents goes into the process and product design, including fluid flow, mass transfer, heat transfer, and separation calculations. Well, if you recall, in one of the slide I said, theoretically millions of ionic liquid feasible. When millions of ionic liquids are feasible, we don't have that much time, that much manpower, and that much fund resources to study all of them. So we need to systematically study some class or within the class, subclass, and few compounds or few ionic liquids, and then develop either structure property correlation or group contribution methods or computational techniques to predict their properties. Well, I put some of the instruments in my laboratory and the collaborator laboratory and the institute's central facilities, but you see everywhere I put accuracy. So wherever in the physical chemistry or any science, once you put a data, it has to be presented with units if units are available, and other than units, conditions has to be mentioned, like what conditions this has been measured: temperature, pressure, concentration, or mole fraction, and accuracy at the confidence level. What, how much accuracy is there? It's not the simply three measurements and average, but accuracy, overall combined accuracy, or the what you call error, combined error, you have to put. Then only that data has a meaning. And this data should be reproducible across the globe, anywhere, in the lab, in the same conditions. Well, I generally say to my students in Hindi, दुश्मन का दुश्मन दोस्त होता है. What we say that enemy's enemy is a friend. When you have a error in the numerator and error in the denominator, the values may cancel out, but error will not cancel out. So दुश्मन पे दुश्मन दोस्त होता है, लेकिन here error पे error cancel नहीं होता है, error दुगना होता है या उससे ज्यादा होता है. So errors will never cancel out, they propagate. One need to pay attention in error propagation. Because of I am in the board, or I am in the team of the JCED editorial board, so I would like to emphasize this specifically whenever data is concerned. I'm happy to announce more than 7,500 data measured in our laboratory has been included in the NIST. And now, before going to applications, let me tell one line, one or two lines. I'm not going into the details of the mechanism of any of these applications. Our core strength is designing ionic liquid for a task-specific application with the task-specific properties, and have an extensive database, and then collaborate with the other scientists from chemistry, physics, biology, biotechnology, or engineering, chemical, petrochemical, metallurgy, mechanical, and facilitate how this basic scientific research can be go for applied scientific research or the technological applications. And I will only show how, without changing the existing process, by adding ionic liquid in a trace amount as an additive or other way in small amount, how it can boost the final products. So we need not to worry about the cost, and we need not to worry about the viscosity. Well, what is yet to address is the circularity or the recyclability or reusability. We have attempted, but that is the area where one can go more. And hope I will end in 3-4 minutes. I will spend 30 seconds each application, some 6 application, then I will go to the end. First one, enhanced oil recovery, where Oil India Limited has provided us SARA analysis. This is an industrial project with my colleague Jitendra Sangwai, who sits in a petroleum engineering division of the ocean engineering department, and we have done this project collectively. 7% of asphaltene is holding large amount of alematics and aromatics, and that's the reason the tank bottom sludge stays here. And cleaning using the conventional surfactant systems or the patented system where they have mostly toluene or dodecan based solvent with some surfactant, or heating with the coil will not work so often. Well, so we have shown that in the existing system where they use toluene, heptane, decane, when you add trace amount of ionic liquid in this ratio 0.1 to 1 to 100 solvent, we saw the solubility enhancement up to 60%. So we have not changed their solvent system. We have only added to the existing solvent some trace amount of ionic liquid, and this we confirm through IR. You can see bending frequency and stretching frequency 1450 and 2950. The black one is sludge, the red one is sludge, and the solvent in this case toluene, and then along with the toluene you added ionic liquid, in this case BMIM PF6. Well, we also confirm with the NMR. So now we have 3 proofs: UV visible, NMIR, and NMR. We are damn sure it is enhancing up to 60%, and by only taking small ratio. Now the question is how this small ratio is helping. So we have provided plausible mechanism that the lone pair on the asphaltene, this is only representative, okay? On a heteroatom of the resin, maybe on sulfur or nitrogen or oxygen, it will be attacked by ionic liquid, probably cation or anion or both. So we are not sure because we need to do more computational study to understand which group is attacking the lone pair. But this may, once this IL and asphaltene are in a contact, this make asphaltene or resin to leave saturates and aromatic apart. So the remaining part is done by the solvent, not by the ionic liquid. Well, similarly, for enhanced oil recovery, we showed that from the optimized system, 52%, 20% recovery is enhanced from the crude oil in this model bed. And the reason is a simple surface tension. When you see the interfacial tension between crude oil and water, and this is the crude oil and water interfacial tension, and by adding a small amount of ionic liquid, this can go even half or less than half, and that's the reason for high enhanced recovery. Well, extraction of lanthanide and actinide from high level liquid waste, this is the conventional solvation mechanism. When you add small amount of ionic liquid, in addition to solvation, you have cation and anion exchange, and that leads to threefold distribution ratios. I know I'm going quickly, but as I told you, my intention is to show in the existing system without compromising on the final product or the yield, how we can reduce the volatile organic compounds quantity required by adding the trace amount of ionic liquid, and how basic science or the basic property study will help to together collaborate with industry and the engineering so we can go for the next step. This is a refrigerating system where we have shown first time with the mechanical engineer group that in the vapor absorption refrigeration system, water also can be used as a co-solvent up to 20% along with the ionic liquid, and the coefficient of performance is comparatively okay with the lithium bromide and water conventional system. However, circulation ratio is slightly high. That means the refrigeration system size will be high, which we can be addressed further research. We couldn't go more than 20% because that was carrying over to condenser and evaporator, and it may damage the systems. And this was the first report in the vapor absorption refrigerator systems. We can use ionic liquid and water as a co-solvent. Similarly, we work on polarity, and next to OHNO, we were the second group to show the relation between solvatochromic parameters and the refractive parameters. And we also work on engine oil kind of things, the conventional therminol and some of the proteoionic liquids. All the properties are much better or comparable with the conventional therminols or what you call engine oils, except the viscosity. Hope we can address, or somebody can take it forward and address this issue also, and can be a more environmentally benign. Of course, then we have to worry about the cost later on. Similarly, dye-sensitized solar cells where volume will expand in the daytime and contrast in the compress in the night time. This may lead to a leakage. Gradcell has worked extensively on this dye-sensitized solar cell, including using ionic liquid. And to promote this iodide triiodide redox process, we are also looking for ionic liquids based on iodine, and it is working well. And we also look for extracting model compounds or even various amino acids, alkaloids, and phenolics from the aqueous waste or bio waste. This is a aqueous biphasic systems where the both part are water rich and they still separate out the phase due to polarity difference, and we have to choose the salts accordingly, and then we can extract from one phase to other phase, and this can be one of the most green method where both the phases are water rich, where this follows similar to Hofmeister series for a protein like salting out and salting in effect, and anion size or the cation charge high, the extraction capability high, and the hydrophobicity high, extraction capability high. We work for extracting various these model compounds. However, we have not gone to the actual system, but there are many people working on these aqueous biophysics systems for extracting these value-added products. Well, we also worked on desulfurization of the model fuel and CO2 absorption. Mechanism is something similar to our primary, secondary, and tertiary amine or monoethanol amines. More than absorption, we need to address the desorption, whether it is feasible. The highest energy in the conventional system goes for the desorption. So, though we have not achieved any great success, but this is also one of the avenue where people are looking. Can we add ionic liquid to the existing monoethanol amine system and can enhance absorption? More than enhancing absorption, can we make less energy required for desorption? Well, I skip few of them and we'll go to the end. This is the book I showed, and then the last slide I prefer to say that theoretically millions of ionic liquid feasible, and most of them can be a liquid at room temperature. And in search, I believe one can find alternative for anything. If it is too optimistic to say anything, I would rather say many things. One can find alternative for many things. And this message is for the young researcher and the students: be positive, no negative in research. And if you see, at least forget about, as I told you, not only government, academician, and industry should work towards sustainability and the green chemistry. As a citizen or a society also should work. If you see how much percentage of these polymers have been recycled, it's very, very, very small number. And at least we can change our lifestyle to the greenery, saying no to single-use plastic, or we use multiple times, or segregate the waste, or we use the bottles or refillable. How many supermarkets have been allowing us to refill with our own jars instead of the plastic one? We can take glass, or can we take our own bag, or we say no to plastic straw, can we use metallic straw, or can we say no to this, all the plastics? Anyway, so this should be our lifestyle for the zero waste. And 7R principle, I do not want to repeat, but it's better as much as possible to refuse when you don't need, reduce, reuse, repair, re-gift it, recover it, recycle it, or at least whatever we are doing, we should rethink. Can we do better way? And I feel in the forthcoming decades, universe and all over the globe, people will face most of the challenges, and the needs would be in the energy, environment, water, food, and health sectors. In all these sectors, we need to provide the sustainability, and we work towards sustainability. And then we should not compromise with the growth, but we should not compromise with the sustainability also. And the chemist has to play a key role. Thank you all. I would like to thank my entire group, and this is my email ID. If you do not get opportunity to ask questions now, you can write to me, gardas@iitm.ac.in.